So what we'd like to understand is how current gets through this device, because what we'd like is its current voltage relationship. And what we've found here is we have more of a voltage charge relationship. Here we have some plus charge, and here we have an equal amount on the other side, negative charge. What we find in these devices, if you took this into the lab and you started putting various voltages across it, and you measured the charge that was accumulating on these plates, you'd find the two were linearly related. And that tells you all of a sudden that you found the interesting thing. And so we can write down that linear relationship. The charge that builds up on one of these plates will be found to be proportional to voltage, and so we'll make up a proportionality constant. Just writing the units, remember this is in coulombs, C for coulomb. This is in volts, V for volt. And this, we got to give it a new name, and it's named for Michael Faraday, and it's farads. And therefore, a farad is 1 coulomb per volt. That's the fundamental units. Just like ohms, it's not a fundamental unit. It's just convenient to have. So this is the key relationship which determines how capacitors work. It's not, however, the current voltage relationship we wanted. It's just the foundation of how they work. So next, we'll figure out how to get the current voltage relationship here. To do that, we have to remember how to get current in here, how to find current in these expressions. And if you remember that the unit of current, amps, equals coulombs, oops, sorry, not charge, but coulombs, so I'll make that a C, coulombs per second, charge per time. Now that's our basic unit. But what that tells us, if we want to think about as this charge is building up as a function of time, due to maybe some voltage, which is a function of time, we need more than just this unit definition. We need to do a little calculus. The charge is the time rate, sorry, the current is the time rate of charge, time derivative of charge. So if we drive a current in here, and now we have to really label everything as a function of time, because these are time-dependent devices. They have a history. The amount of charge that's built up on the plates is going to be the time derivative of the charge is going to be equal to current. If there's a constant current coming into the device, the charge must be building up linearly, because remember, the charge can't go anywhere. If we have zero current on the device, we could still have a charge, a fixed charge, it's just not changing. Both of those should make sense as derivatives. So if we have that the current going into the device tells us the time rate of change of charge, we're filling or emptying the charge bucket, and the current tells us the rate at which that's happening, now we have the things we need. Because if we put these two relationships together, in particular, we insert that charge in this expression, we get the IV relationship we were looking for. C is presumably a constant. It's a factor, a feature of the device. And the current equals C times the time rate of change of the voltage. That is the IV relationship for a capacitor. And notice it's quite fundamentally different than a resistor. A resistor is an instantaneous relationship. V equals IR. And if you think of V and I being time-dependent functions, they would always be identical. They're different only by the proportionality constant, the resistance. For a capacitor, its current voltage relationship, a different one, is related to this capacitance in units of farads. And it says that the current is related to the time rate of change, the derivative of the voltage. That is a very different thing, and has big implications for how we'll use these devices, and makes us able to create much more interesting and complex circuits using capacitors than we could only with resistors.